In this video, we will talk about properties of the Riemann integral. First, we will review the definition of the Riemann integral as well as this theorem, which gives us a condition for checking if a function is integrable. Then we will look at properties of the Riemann integral, which consist the properties in these 5 theorems. So the first theorem that tells us that if f is a monotone function on a closed interval, then the function is integrable. The next one tells us if f is continuous on a closed interval, then it is integrable. The next theorem tells us if we have two integrable functions, first if we multiply the function by a constant, that we can just pull out the constant, and the sum of two integrable functions is just the sum of the two integrals. We also look at another theorem that lets us split up the domain. So if our interval is from a to b, we can split that up into a to c and then c to b. And then last, we'll look at function composition and how that affects integrability. First, we will review the definition of the Riemann integral, and I have taken this information here from our last video, and we were considering a function f on an interval ab. So here I have my interval ab, and the first thing we did in our last video was we talked about partitioning ab, and we partitioned it into points x0, x1 up to xn, so that we would have n intervals. Next, I have the capital Mi, or the maximum of the function, that is the sup of f of x for x in the interval x sub I minus 1 to x sub I. So for this first interval, it looks like our maximum is here at height f of x would be m1. Maybe over here, for this interval, it looks like our maximum is over here at m4. Similarly, I define the minimum, lowercase m of I of x, as the infimum of f of x for x in the interval. So here, the infimum looks to be something like at m4. Here, the infimum on this interval looks like it's at m3. Next, we define the upper sum of f with respect to p. So again, with respect to partitions, right? If you have a different partition, you will get different mf's. Little n, capital N, lowercase. So the upper sum of f with respect to a particular partition is equal to, you sum up all the maximums times the delta x. So basically you're summing up all the areas of the rectangles formed by the maximum height in the interval times the width of the interval. And similarly, you can have a lower sum with respect to the partition where you sum up the rectangles and you take the height to be the infimum, or the lowest point in the interval, times the length of the interval. And finally, we get to this LF and the UF in our definition of the Riemann integral. So UF is the infimum of all the upper sums with respect to all the different partitions. Remember, the upper sum is dependent on the partition. So if you look at all the different upper sums with all the different partitions, the smallest one is then the UF, or the upper integral. Similarly, the lower integral is if you look at all the lower sums and you take the sup. Here it is, LF is the sup of all the lower sum with respect to all the different partitions of AB. So if these two are equal, the lower sum and the upper sum, the lower integral and the upper integral are equal, then their common value is denoted with this normal integral notation, and it is called the Riemann integral. And the last thing we have for review is, this is the definition of the Riemann integral, but sometimes it's not necessarily easy to use the definition to prove something is a Riemann integral. So we have this theorem, which gives us a condition to check to see if something's integral. So if f is bounded on the function ab, then f is integrable if and only if for each epsilon greater than 0, there exists a partition such that UFP minus LFP is less than epsilon. In other words, the difference between the lower integral and the upper integral can be made arbitrarily small, because eventually you want them to be equal. As we move forward with some more complicated proofs, it's very important that this vocabulary is something you're comfortable with. The last thing to review is the proof strategy. So when we want to prove something is integrable, we're going to either use this definition here of the Riemann integral, that the lower integral is equal to the upper integral, then we say that it's integrable. Or we are going to use this theorem here with the condition for integrability. That is, if f is a bounded function on the closed interval ab, then f is integrable if and only if for each epsilon greater than 0, there exists a partition P of ab such that the upper sum minus the lower sum is less than epsilon. In other words, it can be made, this difference here can be made arbitrarily small. Another point is we often start with the partition because both of these definitions and theorems, they both involve partitions, since the lower integral and upper integral relies on the partitions as well. So we often start with partitions, and if there's no partition given, an easy thing to do is divide the interval into n equal intervals. So if your interval is 0 to b, your partition can be 0, b over n, 2b over n, up to n minus 1 times b over n, and then 1 as your final endpoint. And then the width of each is b over n. Another point, I should say, sometimes you use a refinement or some other union or combination of partitions because it is that your particular proof kind of demands it or asks for it. Another kind of thing to do in proofs is after you kind of set things up, you often have to do something clever. And so the idea is here are a few tricks, and as you go through and do more examples, you should increase your bag of tricks so that they're ready for you. The first one is if a function is increasing, the maximum of the function is always going to be towards the right. So if you're on the interval x of I minus 1 to x of I, the maximum, if your function is strictly increasing, is going to be at x of I on the rightmost endpoint, f of xi. The minimum is going to be on the leftmost endpoint, f of xi minus 1. Also, changing indices of summation. If you want to combine a capital F of xi minus 1 with something with an x of I, you can change this indice from x of I minus 1 to f of x of I. But what that means is instead of starting at 1, you have to start 1 back. Since you added 1 to here, these indices have to subtract 1. So you would go from I equals 0 to n minus 1 instead of I equals 1 to n. There's also telescoping series, which you should recognize. So if you have a sum and you have an x of I, and it's minus f of x of I minus, in this case it's 1, but it could be 2, 3, or any other natural number, you'll probably get some cancellation, or you will get some cancellation. So I expanded this function out here. So when I is equal to 1, we get f of x1 minus f of x0. When I is equal to 2, you have f of x2 minus f of x1, etc. And so what you can see is things will start canceling out. So this first term will cancel with the second term. This first term cancels with this second term. This first term will cancel with the second term somewhere in here. And this second term will cancel with some other first term here. And what you're left with are just these two terms. So it's collapsed down like a telescope. And then the last trick is if Q is a refinement, then these sort of inequalities or things that you want to come naturally to you. So the lower integral is always less than the upper integral because the upper integral uses the max on the interval in its sum, and the lower uses the min. So naturally upper is always going to be greater than lower. Then if Q is a refinement, as Q gets refined, the lower integral gets closer to the upper integral because you're getting closer to the lower and upper being equal, as we have here in this the definition of a Riemann integral. So the refinement gets closer to the upper integral, meaning it's greater than any other lower sum on a smaller partition. Similarly, the upper interval, if it's refined, is going to get closer to if it's an upper interval, it's refinement, it's going to get closer to the lower. So in other words, it's going to be less than or equal to any other upper sum with the partition P. And then here, L of F is always greater than or equal to L of P because this is the lower interval. It's getting closer to the upper interval, so it's always greater than L of P of any partition. Similarly for U of F, the upper integral is always getting closer to the lower integral, so it's less than or equal to any random upper sum with a random partition. Now that we have the review done, we can look at the first property, the first theorem for properties of the Riemann integral, which is that a monotone function is integrable. In particular, let f be a monotone function on the closed interval ab, then f is integrable. We will start with f is increasing on ab, and the proof if f is decreasing is similar. So we're just going to look at the case of f increasing. So by definition of what it is to be increasing, that means that all of our f of x is greater than or equal to the left-hand endpoint, f of a, which is less than or equal to the right-hand endpoint, which is f of b. And the f of x is less than or equal to f of b for all x in ab implies that f is bounded on ab. So given an epsilon greater than 0, there exists a constant k greater than 0 such that k of f of a minus f of b is less than epsilon. And again, that's because f is bounded and k can be made less than 1. It just has to be greater than 0. Now we're going to let p be equal to the partition x0, x1 up to xn. And we're going to create these partitions such that each interval, each delta x sub I, is less than k. Since f is increasing, we're going to have our infimum of the interval equal to f of x I minus 1. That's the left-hand side of the interval. So here in this part of the interval, you can see the function's increasing. So the lowest point is going to be our leftmost endpoint, which is x sub I minus 1. And our supremum is going to be on the rightmost endpoint, or the f of x sub I. So then our upper sum with respect to the partition minus our lower sum with respect to the partition. Remember, the upper sum is the length of the interval, and for the upper, times the supremum of the f of x in that interval. So that is the sum of our f of xi, our supremum, times the interval, minus the lower sum is our infimum times the interval. And because we chose our delta xi, in other words, we made our intervals small enough that they would be less than k over here in this step, that means this here, the delta xi, is less than k. So this sum here is less than or equal to k times the sum from 1 to n, f of xi minus f of xi minus 1 is equal to k f of b minus a, which is less than epsilon. And just to be clear on how I got from this step here to this step here, we're going to take a closer look at the sum from I equals n of f of xi minus f of xi minus 1. So this here, with the summation, is a telescoping series. And what that means is a bunch of stuff cancels out except the very first thing and the very last thing. So in particular, let's plug in I equals 1, in which case we would get f of x1 minus f of x0. When we plug in I equals 2, so this is plus, and then plugging in I equals 2, we are going to get f of x2 minus f of x1. When we plug in I equals 3, we will get f of x3 minus f of x2, and you can see what ends up happening. This x1 will cancel with this x1, this x2 cancels with this x2, etc. And so the first term cancels with the second term of the next, except with the exception of this one, of the next term. So here, this term will cancel with the second, so this is going to cancel with the second one here, and eventually this one, something will cancel with this second one here, but what is left then at the very end is the f of x0, which is equal to a, because that's the way partitions are formed, that x0 is equal to a, and then f of xn is equal to b. So after we have this telescoping series down to f of x0, which is equal to a, because that's how partitions are formed. The first x0 is always equal to a, and then f of xn is equal to b is what's left. So this one's positive, so we have f of b minus f of a times k. And if you remember over here, we saw that the k times fb minus fa is less than epsilon. So let me just underline this here. And then finally, looking at this theorem here, the condition for integrability, as long as we have the upper sum minus the lower sum is less than epsilon, there's a partition such that we can make the difference between the upper and lower sums arbitrarily small. And so where did we get this? We have our less than epsilon, our upper sum minus our lower sum is less than epsilon. By this theorem here, that proves that f is integrable on AB. Our next theorem is that continuous implies integrable. So let f be a continuous function on the closed interval AB, then f is integrable on AB. And you know, when I first saw this theorem, I was like, no, we've seen this before. And that's because we saw continuity implies differentiability. Is that right? When you take the derivative. Yeah, differentiability. Now we're talking about integrability. We start with f is continuous on the closed interval AB. So since AB is closed, it contains its boundaries, so it is compact. So f is continuous on the compact set. And by this theorem here that we saw from when we were looking at uniformly continuous functions, we saw that if f is continuous on a compact set, it is uniformly continuous on the compact set. And we're going to use the fact then that f is uniformly continuous, and we're going to apply this definition of uniform continuity. And the definition of uniform continuity says that if your x and y can get to be very small, less than delta, then that means your f of x minus f of y can be made arbitrarily small, less than epsilon, when epsilon is greater than 0. So here I chose, for my x minus y less than delta, I chose the epsilon, the difference between my function to be less than epsilon divided by b minus a. So given an epsilon, I can make an epsilon even smaller. I can choose this epsilon of epsilon over b minus a. And now we are going to create our partition P, x naught, x1 up to xn, partitions A, B, and we're going to create our partition such that each interval is less than delta, and which is a perfectly fine thing to do. So now we let f assume its min and max value on each subinterval, and we know that this is always the case because D is a compact set and f is continuous, so that we know that f assumes a min and max value on the domain. So what that tells us is there is an s of I and a t sub I in each interval such that f of s of I is the infimum and f of t sub I is the supremum of the interval. And since our x sub I minus x sub I minus 1, the length of our interval was chosen to be less than delta, so I highlighted these two things in green so you can see where they tied in. We have that s sub I minus t sub I is less than delta because, well, the whole interval is less than delta, so the infimum and supremum, the distance between them also has to be less than delta. And now our capital M sub I minus little m sub I is between 0 and f of t sub I minus f of s sub I, which again from here, how we chose this, that is this over here, because it was uniformly continuous, we said that we could choose our delta such that the distance between any f of x minus f of y, or the distance between f of x and f of y, is less than epsilon over b minus a. So we bring that over here. And because we want to prove this is integrable, we're going to use this theorem here, the condition of integrability, which is the upper integral minus the lower integral is less than epsilon. So the upper integral is equal to, or minus the lower integral is less than the sum of the supremum minus the infimum times the length of the interval. Because remember, the upper, you're summing up all the rectangles with maximum as the height. The lower, you're summing up all the rectangles with the minimum as the height. So here it is, the height and the length of the interval. But this is less than mi minus little m sub I, they're all less than epsilon of b over b minus a. And then what you have left is the sum from 1 to n of the delta x sub I. But each delta x sub I is the length of the interval, so when you sum them all up, you simply get the length of the interval AB, which is equal to b minus a. And then this b minus a cancels out with this b minus a, and you're left with epsilon. So your upper minus lower integral is less than, here's my less than, epsilon. Therefore, f is integrable on AB by this theorem here. So this was kind of a long proof, but each little step isn't too bad. Did you know integrable is a very hard word to say? For our next example, we are going to look at this modified Dirichlet function over here, where f of x is equal to 1 over n if x is equal to a rational number. When x is equal to m over n, it's rational when this is in lowest terms. Otherwise, f of x is equal to 0 when x is irrational. We want to show that f is integrable. We're going to use the fact that there are only a finite number of unit fractions, i.e. fractions of the sort 1 over n, that are larger than any given positive number. And I'll show you an example of that. These unit fractions will be the capital Mi values for certain subintervals and any partition of 0, 1, where we are considering our function f. But by making the subintervals sufficiently small, this sum here, capital Mi of delta I, which is the upper sum, for these subintervals can also be made arbitrarily small. So let's start. If we're given an epsilon greater than 0, we are going to choose an integer capital N such that our integer is greater than 2 divided by epsilon. So now, as we had mentioned over here, there are only finitely many rational numbers in the interval 0 to 1 that have a denominator less than or equal to n when expressed in lowest terms. So let y equal y1, y2 up to ym represent this set here. So for example, if n is equal to 5, then y is equal to 0, 1/4, 1/3, 1/2, 2/3, 3/4, and 1. And why is that? Because y is the set of fractions that have denominator less than n and is in the interval 0 to 1. So if n is equal to 5, well, it can have denominator 1. Well, first we have 0. It can have denominator 1, and there's only one fraction with, or denominator 1 in the interval 0 to 1 when you reduce everything to lowest terms. It can have a denominator of 2, so you get 1/2, and then, the 2 halves becomes 1. It can have a denominator of 3, so then we get 1/3 and 2/3. It can have a denominator of 4, so we can have 1/4. The 2/4 is the same as 1/2, and then we can also have 3/4. And then, again, we want denominator less than n, so this is our entire set for y. And we are going to use that in our partition. We're going to let n be an integer such that n is greater than 4m divided by epsilon, and m is the number of terms we have in y, or number of fractions we have in y. So we have 1, 2, 3, 4, 5, 6, 7. So m is equal to 7 when n is equal to 5. And we consider the partitions x0, x1 up to xn, where x sub I is equal to 1 over this little n here, and our delta x sub I, the length of our interval, is 1 over n. So again, if, let's say, for example, epsilon is equal to 2, then we need to choose our integer capital N such that it's greater than 2 over epsilon, so it's greater than 1. So we can choose n equals 5, and as we already said, then this would be our list of fractions. And then we're going to choose our little n greater than 4 times m. Here we have 7 terms, so 4 times 7 divided by epsilon, which is 2, 14. So for example, we could choose n equals 15, so this will give us then our partitions. I started 2 drawings to illustrate our situation. This one here, which shows the points of y, 0, 1/4, 1/3, 1/2, 2/3, 3/4, and 1. And then I also started showing this on an interval 0 to 1 divided into 15 subintervals. So I have, my 1/15, 2/15, 3/15, 4/15, 5/15 Over here I have 10/15, and here I have 15/15. And then I put in my elements of y along here, labeled them in blue. So I underlined 0 because that's in y. I have my 1/4, which is approximately here, and this is my first, second, third, fourth interval. And then I have my 1/3, which is on the boundary of the fourth and fifth interval. I have my 1/2, 2/3, 3/4, and 1. And now we will separate the indices of P into two disjoint sets depending on whether or not the subinterval contains a point of y. So A is going to be equal to the subintervals that are disjoint with y, that have no intersection with y, whereas B will be the subintervals that do intersect y. So I underlined the set B. This interval here intersects at 0. This interval contains the point 1/4. This interval here, well, both this interval has 1/3 as the boundary point, and this interval here has 1/3 as the boundary point. This interval has 1/2, and this interval, both of these two intervals have 2/3 as a boundary point. This interval has 3/4, and this last interval has a boundary point of 1. And all these numbers in blue or underlined in blue are in y. So that's how we were going to separate our two sets of intervals and divide it up. Looking at our function, we can see if x is irrational, it is not going to contribute to our upper or lower sum since f of x is equal to 0. So we are going to focus when x is rational, and we have these two separate sets, a and b. So when we are looking at set A, we know that every rational in this interval has a denominator greater than or equal to n, which over here for this example we were looking at is equal to 5, and remember we set n to be greater than 2 over epsilon. So we chose n equals 5. So we want to find a rational that is not in y. So for example, I just picked x equals 2/15, right, because it's not in any of the blue areas, which is b. So at x equals 2/15, my f of x, since 2/15 is in lowest terms, is equal to 1 over n, which is equal to 1/15. Because we're in lowest terms and the denominator is greater than n, and remember in this example n is equal to 5, we know that our f of x then, which is just equal to 1 over n, is our maximum is always going to be less than or equal to 1 over our capital N. So our supremum of the interval is going to be less than 1 over capital N. And then because of how we chose n, that means it's going to be less than epsilon over 2. And again, because we chose n to be greater than or equal to 2 over epsilon. So what we have is our maximum, our supremum of the interval is less than epsilon over 2. Looking at now the set B, which contains the points y, first we want to note that each yi can be in at most 2 of the subintervals. So for example, if we look at 1/4, it is in exactly one subinterval between, this is 1/15, between 3/15 and 4/15. However, if we look at 5/15, that is in 2 subintervals. The subinterval as the right-hand endpoint of the subinterval from 4/15 to 5/15, and as the left-hand endpoint of the interval between 5/15 and 6/15. Hence, there are at most 2m, m being the number of elements in y. There are at most 2m subintervals of B, each with length 1 over n. We know that m sub I is always less than or equal to 1 because how this is defined here, right? Because it's equal to 1 over n when we're in lowest terms. So it's always less than 1 because also our interval only goes up to 1. So since the supremum of our interval is less than 1, that means the sum of our supremum times the length of our interval is going to be less than just the sum of the length of our intervals. And the length of our intervals, when we sum those all up, those are equal to, now we have 2m intervals, each with length 1 over n, so that will give us 2m over n. So this length here is less than this, because they're at most 2m. And then this here, from how we chose our little n, the length of our interval, n was greater than 4m over epsilon, that means this sum is less than 2 times epsilon over 4, which is equal to epsilon over 2. Which means that our upper sum is less than or equal to epsilon over 2 when we're at B, when we're in the set B. And for set A, we also have that our upper sum is less than epsilon over 2. Then we also know our lower sum is equal to 0 because of the density of irrational numbers and the real numbers, our infimums are always going to be equal to 0. So our upper sum with respect to P is the sum we have in A plus the sum we have in B, which are both bounded by epsilon over 2. So the upper sum is less than epsilon minus 0, which is just still less than epsilon. And by our theorem, that means we can say that f is integrable. Our next theorem says that if f and g are integrable functions on a, b, and k is a real number, then kf is integrable, and the integral of kf is equal to k times the integral of f. Also, if f plus g is also integrable, and the integral of f plus g is equal to the integral of f plus the integral of g. And we will do our proofs. When k is equal to 0, everything's 0 and the result is trivial. Next, we will consider k greater than 0. We will look at a partition, and we will use the fact that if we're looking for the supremum of k times a function, we can look for the supremum of the function and multiply the k later, so we can pull the k out. So that'll affect when we look for our upper sum, when we sum up all these supremum, then we can also just pull out the k. We can sum up our m sub i's and pull the k out, multiply by k later, which will also then affect our upper integral, so we can multiply by the k afterwards. We can do a similar argument until we get to the lower integral of kf is equal to k times the lower integral of f. And then because f is integrable, the lower integral of f is equal to the upper integral of f, and then from this statement above, we have that's equal to kf. Hence, we have the lower integral of kf is equal to the upper integral of kf. Hence, kf is integrable. And here is our final statement. For k less than 0, it's similar, so I won't go through it, but I do have some of the key points outlined here. Now we will consider the proof of part B, that the integral of f plus g is equal to the integral of f plus the integral of g. The first note we have is that the sup of the function f plus g over a domain is less than or equal to the sup of f plus the sup of g. And I have this picture to illustrate why that is. I have a function f that reaches its peak at x equals 3, and its peak is equal to 4. I have g here, it reaches its peak at x equals 3, and its peak is at 2, or g of 3 equals 2. So sup of f plus g, and we can just look, because their peaks line up, it's going to be at f of 3 plus g of 3, so it's equal to 5. But now what I'm going to do is I'm going to take this function g, and I'm going to shift it over by 2 units. So its peak, its max, its sup no longer corresponds with the sup of f. And I'm just going to call this new g, g prime. So you can see now, I could add up point by point of f and the g prime to see what the function looks like. But hopefully you can see that the sup of f plus g prime now is going to be less than just the sup of f plus the sup of g, again because their peaks no longer line up. So that's where this expression comes from. From this inequality, we get that the sup of f plus g, which is equal to our capital M sub I, f plus g, is less than capital M sub I f plus capital M sub I g. And since these M sub i's are the things that are summed up when we get our upper sum, that will imply that our upper sum of f plus g with respect to that partition is less than or equal to the upper sum of f plus the upper sum of g. And similarly, we could do the same thing with the infimum and the lower sums. Given this theorem, the condition for integrability, if f is bounded on AB, then f is integrable if and only if. For any epsilon greater than 0, there exists a partition such that the upper sum with respect to the partition minus the lower sum with respect to the partition is less than epsilon. So I am going to apply that to f and g because they're both integrable. So I'm going to have a partition P1 to apply to f and P2 to apply to g. So directly applying this, and in this case, the form is where we add L, the lower sum to both sides. So we have the upper sum of f with respect to P1 is less than the lower sum of f with respect to P1 plus epsilon over 2. So remember, given any epsilon, we can also do this for epsilon divided by 2. And we do something similar for g. Now we are going to let P be the common refinement of P1 and P2. And then we have our same two statements here that the upper sum of f with respect to our partition P is less than the lower sum of f with respect to our partition P plus epsilon over 2. And the same thing for g. The upper sum of g with respect to P is less than the lower sum of g with respect to P plus epsilon over 2. So we have these two statements, and now we want to combine this with what we have up here. So our upper sum of f plus g with respect to P, so that's our upper sum with f plus g with respect to P, is lower than our upper sum of f plus upper sum of g. So is less than or equal to upper sum of f with respect to P plus upper sum of g with respect to P. Now when I add this, and I'm going to substitute this expression, I'm going to substitute lower of f with respect to P plus E2 for this upper of f respect to P, and I'm going to replace the upper of g with respect to P with is less than lower of g with respect to P plus epsilon over 2. The two epsilons over 2 combine, and I get this statement here. So what I have then is this is going to be less than or equal to, again by this statement up here, the combination of the lower of f plus g with respect to P plus epsilon. Hence, f plus g is integratable. Now that we know it's integratable, we want to know what it integrates to. In other words, we need to prove this formula up here that the integral of f plus g is the integral of f plus the integral of g. Since f plus g is integratable, that means this integral here, the Riemann integral of f plus g, is equal to the upper integral of f plus g. And since the upper integral is the infimum of all the upper sums of f plus g with respect to all the partitions, we have this inequality here. And from our work up here, we have the upper sum of f plus g with respect to the partition is less than the lower sum of f with respect to P plus the lower sum of g with respect to P plus some epsilon. That, in terms, is less than or equal to the lower integral of f plus the lower integral of g plus epsilon. And here, because f and g are integrable, the lower integral is equal to the integral, the Riemann integral of f, and the lower integral of g is equal to the Riemann integral of g plus epsilon. So this is the first inequality we have, that the integral of f plus g is less than or equal to the integral of f plus the integral of g plus epsilon. Similarly, we can look at the integral of f plus g and compare it to the lower integral of f plus g to get this chain of events here, so that we have the integral of f plus g less than or equal to the integral of f plus the integral of g plus epsilon, and greater than the integral of f plus the integral of g minus epsilon. And what we're left with is the integral of f plus g is equal to the integral of f plus the integral of g, which is exactly what we wanted to show. Our next example, suppose f and g are integrable on AB, and f of x is less than or equal to g of x for all x in AB. We want to prove that the integral of f is less than or equal to the integral of g. And I have this little drawing that I use to guide me. We are going to start by partitioning the interval, and then we are going to note for each interval x of I minus 1 to x of I that because f is less than g for all x, then our sup of f will always be less than the sup of g. And just looking at this kind of graphically, here I have drawn f, and it's always less than g. Sometimes f might have a maximum, a relative maximum here, where g is kind of declining, but whatever happens, g is always above f. G is always greater than f, which means for any given interval, so like say this interval here between x1 and x2, the maximum of my g of x is always going to be greater than my maximum value of f of x. So that's what I have written here. And now we can look at our upper sum. We could have looked at our lower sum, but I chose to look at the upper sum. So when we sum all these maximum heights times the interval, we will find that the upper sum of f with respect to p is always going to be less than the upper sum of g with respect to p, which will tell us that the upper integral of f will be less than or equal to the upper integral of g. And finally, because f and g are integrable, this upper sum, this is also why we could have done lower sum, is equal to the Riemann integral of f, and that's less than or equal to, and our upper sum of g is also equal to the Riemann integral of g. And we have proven what we wanted to show. And we have another theorem and another theorem to prove. I think we only have 2 more theorems left. So anyway, if we have a function that's integrable over a, b, f is integrable on both AC and CB. So they have this common point, C. Then f is integrable from a to b, and furthermore, the integral from a to b is equal to the integral of f from a to c plus the integral of f from c to b. Something you probably know from first year calculus. Actually, you probably knew all of this stuff from first year calculus. And no surprise, we are going to do a proof, and you could probably guess how we start that proof. We start it with a partition. And I have this little drawing over here because I really like it a lot. So we are going to have a partition P1 of AC and a partition P2 of CB, and we're going to be given an epsilon, and by our definition, since f is integrable, which we are given here in our theorem, f is integrable, that means that our upper sum of f with respect to P1 minus the lower sum of f with respect to P1 is less than epsilon over 2. So we're given an epsilon. We're going to make it even tighten that restriction to epsilon over 2. We'll do the same thing for P2 over CB. That is the upper integral of f with respect to P2 minus the lower integral of f with respect to P2 can be made less than arbitrarily small. The difference between these two can be made arbitrarily small, and we're going to choose to make it smaller than epsilon over 2. Now we're going to consider a new partition P as the union of P1 union P2. So P is a partition across AC union CB. In other words, it's a partition over AB. So when we look at the upper sum of f with respect to p, and again, p is our union, minus the lower sum of f with respect to p, well, our upper sum is equal to the upper sum of f with respect to p1 plus the upper sum of f with respect to p2, and then our lower sum here of p is equal to the lower sum with respect to p1 minus the lower sum with respect to p2. I'm going to rearrange my terms. I'm going to rearrange my P1s together. I'm going to arrange my P2s together so that this here, my upper sum of P1 minus my lower sum of P1, which is what I have up here, is less than epsilon over 2. And my upper sum of P2 minus my lower sum of P2, which is somewhere here, is less than epsilon over 2. So together, they're less than epsilon. And that is exactly what I need to show, that this upper sum of f with respect to p, the partition that goes from a to b, minus the lower sum of f with respect to p, that goes from a to b, is less than epsilon. And so we have shown that f is integrable over the interval a, b. To find what it integrates to, in other words, to verify this formula here, we note that the integral, the Riemann integral of f from a to b, is less than or equal to the upper integral of f with respect to the partition p, which is equal to the upper integral of f with respect to p1 plus the upper integral of f with respect to p2, and that is less than the lower integral of f with respect to p1 plus the lower integral of f with respect to p2 plus epsilon. And this epsilon here bit, that just comes from this theorem here where we move the lower integral over to the, and add it to the epsilon. And the lower integral is less than or equal to, and this is p1, the Riemann integral from a to b of f, and this lower integral of p2 is less than the integral from c to b of f plus the epsilon. Similarly, we have this string of inequalities that put the integral from a to b as greater than or equal to the integral from a to c of f plus the integral from c to b of f minus epsilon. Combining these two results here, these two inequalities, we get the integral of f from a to b is equal to the integral of f from a to c plus the integral of f from c to b, which is exactly what we wanted to show. This last theorem we are not going to prove, but it is an important theorem and we will do examples. It is about function composition and how it affects integrability. So suppose f is integrable on AB and g is continuous on CD, where f of AB is a subset of CD. Then g composed of f of x is integrable on AB. And note, the composition of two integrable functions may not be integrable, right? We have to have these conditions here. G is continuous on f of AB, which is a subset of CD. Our corollary, let f be integrable on AB, then the absolute value of f is integrable on AB, and we have the absolute value of the integral of f is less than or equal to the integral of the absolute value. Our next example is suppose f is integrable on AB and let n be a natural number. Use the theorem about function composition and integrability, which is this theorem over here, to prove that f to the nth power is integrable on AB. Since f is integrable, then f is also bounded on that interval. So there exists some number, capital B, greater than 0, such that the absolute value of f of x is less than or equal to capital B for all x in the interval AB. So we're going to find a function g on negative b to r by g of t is equal to t to the n, since we're really trying to evaluate f to the n. Then g is continuous on negative b to b, and g composed of f is equal to f to the n. Thus, by this function composition here, it says that if f is integrable on AB, which is what we have, and g is continuous, which we had determined, then g of f of x is integrable. So g composed of f, which is equal to f to the n, is therefore integrable. That's it for the main topics. For review, I have 2 problems for you to try, so pause the video, give the problems a try, and on the next slide I'll have solutions. Here are the solutions to the 2 problems. And that's it for this video. Thank you for watching.